Imagine looking up at the night sky and seeing not just scattered stars, but dense, shimmering orbs of light, each one a city of stars packed so tightly together, they outshine entire galaxies. These are globular clusters, ancient relics of our universe, some nearly as old as time itself. They've witnessed the birth and death of countless stars, harboring secrets that challenge everything we thought we knew about space. And yet, despite their age and brilliance, they remain some of the most enigmatic structures in the cosmos. What bizarre truths lie hidden within these celestial time capsules? For centuries, astronomers assumed globular clusters were simple, predictable systems, orderly collections of stars orbiting in perfect harmony. But the deeper we look, the stranger they become. Some of these clusters defy the laws of physics, hiding black holes where none should exist. Others contain stars that shouldn't have formed at all, or mysterious gaps in their populations that scientists still can't explain. And then there are the rogue stars flung out at unimaginable speeds, leaving trails of cosmic breadcrumbs that hint at violent, unseen forces lurking within. These aren't just clusters, they're cosmic puzzles, each one rewriting the rules of stellar evolution. Today, we're diving into 30 of the most baffling discoveries about globular clusters, revelations that will make you question how well we truly understand the universe. From stars that burn hotter than logic allows to dark matter oddities that defy detection, these clusters are treasure troves of cosmic anomalies. Why do some of them appear younger than they should be? How do they survive collisions that should tear them apart? And what do their strange, twisted orbits tell us about the invisible forces shaping our galaxy? Buckle up, because by the end of this journey, you'll never look at the night sky the same way again. One of the most startling revelations about globular clusters is the existence of stars that simply shouldn't be there, at least not according to our current understanding of how stars age. These celestial rebels, known as blue stragglers, burn hotter, brighter, and bluer than their neighbors, standing out like energetic teenagers in a retirement home. Their presence is a direct challenge to everything we know about stellar evolution. In a cluster where all stars were born around the same time, often over 12 billion years ago, why do some still shine with the vigor of youth? It's as if nature left a glaring clue in the cosmos, daring us to solve the mystery. The most widely accepted explanation is that these stars aren't actually young at all, they're cosmic phoenixes, reborn through violent encounters. One theory suggests that two older stars collided, merging into a single, hotter, more massive star. Imagine two slow-burning embers smashing together to create a roaring flame. Another possibility is that one star in a binary system siphons material from its companion, rejuvenating itself with fresh fuel. It's like a vampire star, stealing life from its neighbor to delay its own inevitable fade into darkness. But the strangest part, some blue stragglers defy even these theories. A few have been found with chemical compositions that don't match expectations, hinting at formation processes we haven't even imagined yet. Are there hidden mechanisms at play, some unknown quirk of physics that allows stars to cheat time? Every unanswered question deepens the enigma, reminding us that globular clusters aren't just relics of the past, they're active cosmic laboratories, rewriting the rules right before our eyes. If blue stragglers were the first cosmic curveballs globular clusters threw at us, the discovery of rogue black holes lurking within them was an absolute game changer. Conventional wisdom said these ancient star cities were too small and too old to harbor anything more than stellar mass black holes, the remnants of dead stars. But the universe loves proving us wrong. Hidden in the heart of some clusters are monstrous intermediate mass black holes, tipping the scales at thousands of times the mass of our Sun. These gravitational heavyweights shouldn't exist here, at least not according to our models. So how did they end up gate-crashing the party? The first clues came from the way stars near the centers of certain clusters moved, like frenzied dancers caught in an invisible whirlpool. Their velocities were off the charts, suggesting something massive was pulling them in, something far larger than a typical stellar corpse. Then came the X-ray emissions, intense bursts of energy that betrayed the presence of black holes gobbling up nearby gas. But the real smoking gun, computer simulations showing these black holes didn't form from single collapsing stars. Instead, they likely grew over billions of years through a brutal chain reaction, small black holes merging, consuming neighbors, and snowballing into cosmic monsters. Picture a game of stellar pinball where collisions are inevitable, and the grand prize is a gravitational titan. What's truly bizarre is that these black holes seem to be both destroyers and architects. Their crushing gravity can fling stars out of the cluster at terrifying speeds, creating hypervelocity escapees. Yet they also appear to stabilize their surroundings, preventing entire clusters from unraveling. It's a paradox that's rewriting textbooks, destructive forces acting as cosmic glue. Even stranger, some clusters show signs of multiple black holes locked in a gravitational tug-of-war, a scenario that should be impossibly chaotic. Yet there they are, defying logic. Astronomers are now racing to understand what this means for our theories of black hole formation. Are these the missing links between small stellar black holes and the supermassive beasts at the centers of galaxies? Could globular clusters be the universe's black hole nurseries? Every new observation peels back another layer of mystery, proving these ancient star swarms are anything but predictable retirement homes for aging stars. They're dynamic, violent, and full of surprises, reminding us that in the cosmic dance of gravity and time, the most fascinating steps are often the ones we never saw coming. If black holes in globular clusters were unexpected, the discovery of planets orbiting stars in these ancient stellar cities was downright shocking. Conventional wisdom said planets couldn't survive here, not in these densely packed, radiation-bombarded neighborhoods where stars brush past each other like commuters in a cosmic rush hour. The gravitational chaos alone should rip any fledgling planetary system apart. Yet against all odds, astronomers have spotted worlds clinging to existence in these hostile environments, rewriting what we thought possible for planet formation. The first hints came from tiny, rhythmic dimming patterns in the light of cluster stars, telltale dips caused by orbiting planets crossing their faces. Finding them required sifting through mountains of data, like listening for a whisper in a hurricane. But there they were, worlds stubbornly holding on in places where theory said they shouldn't last 1,000,000 years, let alone billions. Some orbit pulsars, the zombified corpses of dead stars emitting deadly radiation beams. Others drift through regions so crowded that passing stars should have long since kicked them into interstellar space. Their very existence is a cosmic paradox. How do these planets survive? One theory suggests they're cosmic survivors, born in safer outskirts before migrating inward, protected by sheer luck or some unseen gravitational balancing act. Others might be second-generation worlds, forming from the debris of shattered stars after the cluster's violent early years had settled. Picture a phoenix rising not from ashes but from the wreckage of stellar collisions. The most intriguing possibility, that some globular clusters, despite their harsh conditions, might possess quiet corners where planetary nurseries persist, pockets of stability in a stellar storm. These discoveries aren't just curiosities, they're shaking the foundations of planetary science. If planets can form and endure in such extreme environments, what does that mean for the potential of life elsewhere in the universe? Could radiation-shielded moons or deep underground oceans exist even here? And if globular clusters, some of the oldest structures in the cosmos, harbor planets, it suggests that worlds have been forming almost as long as stars themselves. That's a profound shift in our understanding of cosmic history. Every rogue planet found in these clusters forces us to reconsider the resilience of planetary systems. They're cosmic underdogs, defying the odds and reminding us that the universe always has another surprise up its sleeve. As telescopes grow more powerful, who knows what other impossible worlds might be waiting in these ancient star swarms. One thing's certain, the rulebook for planet formation just got a lot more interesting. Among the many puzzle's globular clusters present, perhaps none is more perplexing than their apparent lack of dark matter, the invisible cosmic glue that holds galaxies together. Unlike spiral galaxies, where dark matter outweighs visible stars by a factor of 10, these dense star clusters seem to defy the rule, containing little to none of this mysterious substance. It's as if someone forgot to invite the universe's most abundant ingredient to the party. This glaring absence throws a wrench into our understanding of how dark matter behaves and what role it plays in shaping cosmic structures. For decades, astronomers assumed dark matter was the hidden scaffolding of all large-scale celestial objects. Its gravitational pull explains why galaxies rotate faster than they should and how vast cosmic webs form. But globular clusters, which can contain millions of stars packed into a relatively tiny space, show no signs of this shadowy influence. Their stars move exactly as you'd predict based on the visible mass alone. No extra gravitational tug, no unexplained velocities. This isn't just a minor discrepancy, it's a direct challenge to dark matter's universality. If these clusters formed without it, what does that say about the rules governing the cosmos? One leading explanation suggests globular clusters might be dark matter deserts, regions where violent interactions early in their history stripped this elusive material away. Picture a cosmic game of pinball, where stars and black holes slingshot around with such force that they ejected the lightweight dark matter entirely. Another theory proposes these clusters never contained dark matter to begin with. Perhaps they formed differently than galaxies, condensing from dense pockets of ordinary matter in the early universe, bypassing dark matter's influence altogether. The implications ripple across astronomy. If dark matter isn't essential for holding globular clusters together, what keeps them intact? Their gravity alone shouldn't prevent them from flying apart over billions of years. Some researchers point to the tight orbits of stars and the gravitational influence of central black holes as potential stabilizers. Others wonder if we're misinterpreting the data entirely. Could dark matter be present but hiding in a form we can't detect? There's even a radical idea that globular clusters might be testing grounds for modified gravity theories where dark matter isn't needed at all. This mystery isn't just academic. It forces us to reconsider how structures assemble in the universe. Are globular clusters cosmic oddballs, or do they reveal a gap in our understanding of dark matter's behavior? Every observation deepens the intrigue, proving that even the missing pieces of the puzzle can teach us volumes about the cosmos' hidden rules. Globular clusters have thrown another curveball at astronomers' stars that break the cosmic rulebook with chemical compositions that simply shouldn't exist. These are not just slightly unusual stars, they're outright rebels packed with bizarrely high amounts of elements like helium, sodium, or even oxygen at levels that defy everything we know about stellar physics. It's as if the universe scribbled over its own laws, leaving scientists scrambling to decode the message. Take helium-rich stars, for example. In a typical globular cluster, you'd expect stars to share similar chemical fingerprints, since they all formed from the same primordial gas cloud billions of years ago. But some stars are practically drowning in helium, burning so intensely that their outer layers should have stripped away long ago. Others show sodium levels up to 100 times higher than their neighbors, like cosmic seasoning gone wildly out of balance. These anomalies aren't just quirks, they're glaring violations of standard stellar chemistry. So what's going on? The leading theory points to a phenomenon called stellar pollution. Imagine an older generation of stars, long since dead, that spewed their chemically enriched guts into the cluster's shared gas reservoir. When new stars formed from this polluted material, they inherited these abnormal element ratios, creating a stellar lineage with forbidden traits. Think of it like a cosmic family heirloom, except instead of antique furniture, it's bizarre chemistry passed down through generations. But here's where it gets even stranger. Some of these chemically peculiar stars aren't just passive recipients, they might be actively altering their own compositions. In densely packed clusters, stars can siphon material from their neighbors or even collide, creating hybrid stars with freakish element cocktails. Picture two stars merging, their atmospheres mixing like paint and producing something entirely unexpected. The implications are staggering. If stars can rewrite their own chemical signatures, it challenges our assumptions about how elements are distributed in the universe. It also raises tantalizing questions. Could these forbidden stars hold clues about the early universe's chaotic conditions? Might they reveal unknown nuclear processes happening deep in stellar cores? Every discovery peels back another layer of mystery, proving that globular clusters aren't just relics, they're active cosmic laboratories where the rules are still being written. Globular clusters present us with yet another cosmic head-scratcher: the baffling absence of supernova remnants. Given their ancient age, these dense stellar cities should be littered with the ghostly echoes of massive star explosions. After all, supernovae are the universe's great recyclers, scattering heavy elements across space in spectacular bursts of light. But when astronomers scour globular clusters for signs of these violent deaths, they come up nearly empty-handed. It's like investigating a crime scene where the weapon, the perpetrator, and even the victim have all vanished without a trace. The numbers make this mystery even more perplexing. A typical globular cluster contains hundreds of thousands of stars, with many massive enough to end their lives as supernova. Over 12 billion years, hundreds, if not thousands, of these explosions should have occurred. Yet modern observations detect almost no supernova remnants, no expanding gas shells, no neutron stars kicking around at high speeds, no telltale chemical enrichment in surrounding stars. It's as if these clusters skipped one of the universe's most fundamental processes. So where did all the supernova go? One compelling theory suggests these explosions happened, but their remnants didn't stick around. In the crowded core of a globular cluster, a newborn neutron star from a supernova could receive such a powerful gravitational kick from nearby stars that it gets ejected entirely, flung into interstellar space at speeds over 1 million miles per hour. Imagine a pinball machine where the ball doesn't just bounce, it rockets straight through the backglass. These runaway compact objects would leave no trace behind, effectively erasing the evidence of their violent birth. Another possibility is even more mind-bending: that some massive stars in globular clusters don't explode at all. Current models predict that stars between 8 and 25 solar masses should end as supernova, but peculiar chemical signatures in these clusters hint that many might have collapsed directly into black holes instead, swallowing their explosive fate whole. It's like a magician's trick where the expected flash and bang never come. The star simply vanishes from the cosmic stage, the most radical explanation. That globular clusters somehow prevented massive star formation altogether after their initial burst. If early supernova or intense radiation cleared out the gas needed to form new heavy stars, later generations might have been exclusively lightweight stars that fade quietly rather than going out with a bang. This would make globular clusters cosmic retirement communities where fireworks are strictly prohibited. This missing supernova problem doesn't just affect our understanding of these clusters, it challenges foundational ideas about how stars live and die. If massive stars can bypass supernova under certain conditions, what does that mean for element formation across the universe? Could entire populations of black holes be hiding in plain sight, born from silent collapses we've failed to detect? Each unanswered question forces us to reconsider how stellar death works in different environments. proving that even the most violent cosmic events can sometimes leave behind the quietest mysteries. Among the many strange inhabitants of globular clusters, none are more dramatic than the hypervelocity stars, stellar outcasts rocketing through space at speeds so extreme they can escape the Milky Way entirely. These cosmic fugitives don't just drift away, they're violently ejected, flung across the galaxy like stones from a slingshot, leaving their birthplace behind at over 1 million miles per hour. Their existence was once thought impossible, yet today, we've traced dozens of these runaway stars back to their origins in globular clusters, revealing a hidden story of gravitational chaos and celestial pinball. The secret to their incredible speed lies in the cluster's dense cores, where black holes and massive stars engage in a relentless gravitational dance. When a star drifts too close to a binary black hole system, the encounter can slingshot it outward with unimaginable force. Picture a game of cosmic billiards where the cue ball is a black hole and the target, the star, gets launched clear off the table. Some simulations suggest these interactions can accelerate stars to speeds exceeding 2 million miles per hour, fast enough to break free from the Milky Way's gravitational grip entirely. But not all hypervelocity stars are created equal. Some follow bizarre, looping trajectories, suggesting they were ejected not by a single kick, but by a series of chaotic encounters. Others bear chemical scars, odd element ratios that hint at violent pasts, like stellar survivors of a celestial demolition derby. One famous example, known as He 0437-5439, races through space at over 1.6 million miles per hour, its path tracing a straight line back to a globular cluster in the constellation Hydra. The implications go far beyond these individual stars. Their escape routes act as cosmic breadcrumbs, helping astronomers map the invisible gravitational landscape of the galaxy. By studying their trajectories, we can uncover hidden black holes or even dark matter distributions that would otherwise elude detection. It's like using a fireworks display to illuminate the shape of the night sky. Each streak of light reveals something unseen. Most fascinating of all, these stars aren't just running away, they're spreading the cluster's influence across the galaxy. As they travel, they carry with them the unique chemical signatures of their birthplace, effectively seeding the Milky Way with traces of globular cluster material. In a way, these runaways ensure that even as clusters age and fade, their legacy endures, scattered among the stars like pages torn from an ancient cosmic diary. Here's one of the most mind-bending puzzles in astronomy: globular clusters that initially appeared older than the universe itself. Early measurements of these ancient star cities suggested ages upward of 14 billion years, a number that flatly contradicted the estimated age of the cosmos at the time, which hovered around 12 billion years. It was like finding a grandfather clock ticking away in a house that hadn't even been built yet. For decades, this discrepancy haunted astronomers, threatening to upend our understanding of cosmic history. How could structures exist before the universe that birthed them? The root of the paradox lay in the methods used to date these clusters. Scientists relied heavily on the behavior of their stars, particularly those in the main sequence, the stable phase where stars burn hydrogen. By comparing a cluster's faintest, longest-lived stars to theoretical models, they could estimate its age. But early models had critical flaws. They underestimated how much heavier elements, like those present in globular clusters, affected a star's lifespan. Metals act like cosmic antifreeze, making stars burn hotter and faster than their purer, hydrogen-rich counterparts. Without accounting for this, astronomers were essentially misreading the star's expiration dates. Another complication came from distance measurements. If a cluster was farther away than assumed, its stars would appear dimmer, tricking observers into thinking they were older and fainter than they truly were. It's like mistaking a young athlete in a distant stadium for an elderly spectator. Perspective skewed reality. Only with the precise parallax measurements from space telescopes like Gaia did we begin to untangle this cosmic illusion. The resolution arrived through a combination of better cosmology and sharper stellar physics. Revised calculations of the universe's expansion rate pushed its age to roughly 13.8 billion years, buying some breathing room. Meanwhile, updated stellar models incorporated the effects of metallicity, revealing that globular clusters, while ancient, weren't quite as old as initially feared. Most now sit comfortably between 11 and 12.5 billion years, still primordial, but no longer time travelers from a pre-universe era. Yet the mystery didn't just vanish, it transformed. The refined ages exposed deeper questions about how globular clusters formed so early and so fast. Some appear to have assembled in less than a billion years after the Big Bang, an eye blink in cosmic time. What processes could build such dense, intricate structures in conditions far more chaotic than today's universe? The answer may lie in the clusters themselves. Their stars lack heavy elements, suggesting they formed from nearly pristine gas, unfettered by the chemical enrichment of later generations. This purity let them ignite and organize with startling efficiency, like sparks catching in dry tinder. Today, the Great Age paradox serves as a humbling reminder. Even our best tools can mislead when we overlook subtle details. It's also a testament to scientific progress, how patient revision and better data can turn contradictions into breakthroughs. And who knows, as we peer deeper into these ancient stellar metropolises, they may yet reveal new wrinkles in time, challenging us once more to rethink the universe's chronology. One of the most revolutionary discoveries about globular clusters shattered a long-held assumption that all their stars formed in a single, frenzied burst of creation early in the universe. Instead, meticulous observations revealed distinct stellar generations nestled within these clusters, like layers of an archaeological dig telling separate chapters of a cosmic story. This wasn't just a minor tweak to the timeline. It upended the idea that these clusters were monolithic relics frozen in time. The evidence came from subtle but unmistakable differences in starlight variations in chemical composition that betrayed multiple epochs of star birth separated by hundreds of millions of years. The smoking gun, stars with starkly different levels of heavier elements like oxygen, sodium, and aluminum. In a true single-generation cluster, every star should share nearly identical chemistry, having formed from the same primordial gas cloud. But some stars flaunt exotic element cocktails, helium-rich or sodium-packed, that could only arise if fresh gas, enriched by earlier supernovae, cooled and collapsed into new stars much later. Imagine a family photo where half the relatives inexplicably wear futuristic attire, hinting they were added generations after the original portrait was taken. These chemical outliers forced astronomers to confront a startling reality. Globular clusters weren't one-and-done creations but complex factories that somehow reignited star formation long after their initial firestorm. Enter the baby boom hypothesis, a theory as dramatic as its nickname suggests. It proposes that some clusters experienced secondary bursts of star formation triggered by extraordinary circumstances, perhaps collisions with giant gas clouds or violent mergers with other clusters. Picture a dormant volcano suddenly erupting anew, spewing fresh stellar material into the cosmic void. Supporting this idea are clusters like Omega Centauri, where stars separate into at least 3 distinct age groups spanning over 2 billion years. Even more telling are younger clusters still embedded in gaseous envelopes, suggesting the process might occasionally repeat in slow motion. The implications ripple far beyond stellar demographics. Multiple generations imply globular clusters were far more dynamic than we imagined, capable of retaining or acquiring enough gas to fuel new star birth despite their intense gravitational environments. It also raises provocative questions. Did some clusters cannibalize smaller neighbors to steal their gas? Could dark matter have played a hidden role in stabilizing these late-stage nurseries? And if stars kept forming, why did the process eventually stop, leaving today's clusters as static-looking fossils? Perhaps the most tantalizing clue lies in the helium paradox, the discovery that younger generation stars often show elevated helium levels. This suggests the later star-forming gas wasn't just sitting around, it was polluted by the violent deaths of the first generation, their ashes recycled into new stellar life. It's a cosmic version of a phoenix rising where destruction fuels rebirth, yet mysteries remain. Not all clusters show these multiple generations, hinting that environment or timing played a decisive role in which clusters got a second act. This discovery didn't just rewrite globular cluster history, it revealed them as cosmic palimpsests, their layers of stars recording eons of change. Far from being simple time capsules, they're active participants in galactic evolution, their complex stellar populations challenging us to rethink how structures grow and adapt over cosmic time. Every new observation peels back another layer, proving that in the universe's oldest neighborhoods, the story is still being written. Some of the strangest cosmic whispers come not from the visible light of stars, but from the invisible crackle of radio waves, and globular clusters have been caught broadcasting signals that defy easy explanation. These mysterious emissions, picked up by radio telescopes around the world, don't match the usual suspects like pulsars or magnetars. Instead, they flicker with patterns that suggest something far more exotic might be hiding among these ancient stars. Take the bizarre case of Glimpse C01, a globular cluster that's been emitting erratic radio bursts for years, each one a puzzle wrapped in static. At first glance, pulsars seem like the obvious culprits. These spinning neutron stars beam radio waves like cosmic lighthouses, and globular clusters are packed with them. But the signals from Glimpse C01 don't behave like any known pulsar. They're irregular, sometimes vanishing for months before flaring back to life with unpredictable intensity. Even stranger, their frequency profiles don't align with the telltale signatures of stellar remnants. It's as if the cluster is playing a celestial game of hide and seek, taunting astronomers with clues that lead nowhere. One radical theory points to dark matter annihilation, the idea that invisible particles colliding in the cluster's dense core could release energy as radio waves. If true, it would mean globular clusters aren't just star cities, but particle physics labs where dark matter reveals itself through subtle, elusive signals. Picture a cosmic radio tuned to a station we can't quite hear. It's static, hiding the secrets of the universe's most mysterious substance, but the plot thickens. Some signals appear to come from empty patches of space within the clusters, regions where no visible object could be producing them. Could these be the echoes of long-dead stars, their remnants warping space-time to create natural radio amplifiers? Or perhaps evidence of intermediate mass black holes, those elusive gravitational ghosts interacting with surrounding gas in ways we've never observed? The most tantalizing possibility, that we're detecting something entirely new, a class of object or phenomenon that doesn't fit any existing model. Glimpse C01's radio murmurs might be the first hints of physics operating beyond our current understanding, a cosmic anomaly waiting for its Rosetta Stone. Until then, every unexplained burst is a reminder that globular clusters still hold surprises, their oldest stars whispering secrets we're only beginning to decode. Not all globular clusters are built the same. Some pack their stars so tightly at the center that you could fit thousands into a space smaller than our solar system, while others appear almost hollowed out, their cores strangely diffused. This bizarre discrepancy has puzzled astronomers for decades. How can these ancient star clusters, born under similar conditions, evolve such radically different hearts? The answer seems to lie in a violent cosmic process known as core collapse, a gravitational dance that can either forge a stellar metropolis or leave it in ruins. The most densely packed cores defy imagination. Take NGC 6397, where stars are crammed so close together that a single light year could contain over 10,000 of them. If you stood on a planet there, the night sky would blaze with stars brighter than our full moon. These ultra-dense cores aren't just cosmic curiosities, they're natural laboratories for studying how gravity warps space and time under extreme conditions. But why do some clusters reach this state while others, like Palomar 5, have such sparse centers that you could fly through them for years without spotting a nearby star? Enter the gravithermal catastrophe, one of the most dramatic theories in stellar dynamics. Picture a cluster as a boiling pot of stars, constantly trading energy through gravitational interactions. Over billions of years, heavier stars sink toward the center like sediment in water, while lighter stars get flung outward. This creates a runaway effect. As the core contracts, its gravity grows stronger, pulling in even more stars until it reaches a critical density. At this point, the core collapses catastrophically, either forming an impenetrable knot of stars or, if conditions are right, triggering a chain reaction that blows the cluster's center apart like a stellar supernova. But here's where it gets counterintuitive. Some clusters bounce back from collapse, their cores mysteriously re-inflating over time. The leading explanation involves black holes, not just as destroyers but as cosmic stabilizers. When multiple black holes form in the collapsed core, their chaotic orbits can pump energy back into the system, pushing stars apart like pinballs in a high-stakes game. It's as if the cluster's heart stops, then restarts with a new rhythm. Other clusters aren't so lucky. Without enough black holes to reverse the collapse, they continue condensing until their cores become almost solid with stars, frozen in gravitational rigor mortis. The strangest twist, some clusters appear to be mid-collapse right now, offering astronomers a front-row seat to the process. Omega Centauri, for instance, shows signs of partial core collapse, its central stars whirling faster and hotter, like water spiraling toward a drain. By studying these cosmic transitions, scientists are rewriting the rules of how stellar systems age. What was once thought to be a one-way street toward destruction is now seen as a complex cycle of collapse and rebirth, governed by physics we're only beginning to understand. This isn't just about star clusters, it's a window into how all gravitational systems evolve, from galaxies to dark matter halos. The same processes that shape these dense cores might dictate how entire structures form and perish across the universe. And with new telescopes peering deeper into cluster hearts than ever before, each observation brings us closer to solving one of astronomy's most enduring puzzles: how chaos and order dance together in the cosmos' oldest ballrooms. Globular clusters may appear as tightly bound islands of stars, but many of them are slowly unraveling, stretching ghostly tendrils across the galaxy that most telescopes can barely detect. These are tidal tails, vast rivers of stars ripped from their parent clusters by the Milky Way's relentless gravitational pull. Like cosmic breadcrumbs, they trace paths through the darkness, revealing not just the cluster's violent histories, but the invisible forces shaping our entire galaxy. The process begins with a cluster's orbit. As it swings close to the Milky Way's crowded center, the difference in gravity between its near and far sides, known as tidal forces, stretches the cluster like taffy. Stars on the outer edges get stripped away, forming elongated streams that can span thousands of light years. Some tails, like those trailing from Palomar 5, are so vast they wrap around the galaxy multiple times, a shimmering veil of exiled stars. Others, like the twin tails of NGC 5466, resemble celestial comet trails marking the cluster's path through space. But these tidal tails aren't just casualties, they're cosmic detectives. By mapping their curves and kinks, astronomers can reconstruct the Milky Way's gravitational field in unprecedented detail. Think of them as high-precision instruments, sensitive enough to detect dark matter clumps or even unseen dwarf galaxies tugging at the streams. One striking example is the GD1 stream, a stellar ribbon so pristine its slight warp suggests it brushed past a massive, invisible object, likely a dark matter subhalo hundreds of millions of years ago. The real surprise, some clusters are losing stars faster than anyone predicted. Take the case of NGC 7982, whose tails stretch so far they've nearly dissolved into the galactic background. Simulations suggest it could completely disintegrate within a billion years, a blink in cosmic time. Other clusters, like Omega Centauri, sport multiple generations of tails, hinting at past close encounters with the galaxy's spiral arms or central bar. Most haunting of all are the orphan streams' tidal tails with no visible parent cluster left. These ghostly rivers of stars, like the famous Jhelum stream, may be all that remains of globular clusters torn apart long ago. Their very existence forces us to reconsider how many clusters the Milky Way has already consumed, and how many more will fade into these stellar echoes. Far from being static relics, globular clusters and their tidal tails are dynamic players in the galaxy's evolution. As they shed stars, they enrich the Milky Way's halo with ancient metal-poor material, a process that's been ongoing since the galaxy's infancy. Every stream is a living fossil, telling a story of gravitational battles fought over billions of years. And with new telescopes like the Vera Rubin Observatory set to uncover thousands more, we're on the verge of reading these cosmic hieroglyphs like never before. For decades, dwarf galaxies were considered the cosmic underdogs, small, faint collections of stars orbiting larger galaxies like the Milky Way. But one glaring problem puzzled astronomers: there simply weren't enough of them. Theories predicted thousands should exist around our galaxy, yet observations found only a handful. The answer to this mystery might lie in the unlikeliest of places: globular clusters. Recent studies reveal that some globular clusters aren't just random star swarms. They're likely the surviving cores of ancient dwarf galaxies torn apart and devoured by the Milky Way's gravity. The evidence lies in their chemical fingerprints. Unlike typical globular clusters, which are made of stars with nearly identical compositions, certain outliers like Omega Centauri and M54 contain multiple stellar populations with wildly different element ratios. This matches exactly what we'd expect from dwarf galaxies, where successive generations of stars would have enriched their surroundings over time. But chemistry isn't the only clue. Many of these clusters also move differently. While most globular clusters orbit the Milky Way's center in predictable paths, these oddballs follow eccentric, tilted trajectories that suggest they weren't born here, they were captured. Simulations show that when a dwarf galaxy falls into a larger one, its outer stars get shredded by tidal forces, leaving only the dense core intact. Over billions of years, that remnant could easily be mistaken for a globular cluster unless you know where to look. The smoking gun: some of these clusters still retain traces of their galactic past. Take Omega Centauri, the Milky Way's largest globular cluster. Not only does it have multiple stellar generations, but it also harbors a rare, intermediate mass black hole at its center, a feature common in dwarf galaxies but unheard of in ordinary globular clusters. Even more telling, its stars rotate in a disk-like structure, eerily reminiscent of a scaled-down galaxy rather than a chaotic star cluster. This realization rewrites the history of our cosmic neighborhood. If globular clusters are the fossilized hearts of devoured dwarf galaxies, then the Milky Way didn't just grow by forming stars. It cannibalized smaller systems, each merger leaving behind a dense, glittering tombstone. That means the missing dwarf galaxies aren't missing at all. They've been hiding in plain sight, disguised as globular clusters all along. The implications stretch far beyond our galaxy. If this phenomenon is common, then globular clusters could be universal evidence of galactic cannibalism, offering a new way to study how large galaxies assemble over cosmic time. Every unusual cluster might be a clue, a relic from a long-dead galaxy that once roamed the cosmos independently. And with next-generation telescopes sharpening our view, we're on the verge of uncovering more of these cosmic imposters, revealing a violent, hidden history written in starlight. Globular clusters aren't just crowded with stars, they're teeming with pairs of them, locked in gravitational embraces that throw these ancient systems into chaos. Binary stars, two stars orbiting a common center of mass, are everywhere in these dense environments, far more abundant than in the Milky Way's open clusters or galactic neighborhood. In fact, some globular clusters host thousands of these dynamic duos, turning what should be serene stellar retirement homes into cosmic mosh pits where gravity's rules get bent, broken, and rewritten. The reason for this overabundance lies in the cluster's extreme density. Stars are packed so closely together that close encounters are inevitable. Picture a crowded dance floor where partners keep getting swapped. Only here, the dancers are massive stars and the music never stops. Single stars frequently get captured into binary systems, either through direct collisions or gravitational theft, where one star steals another from its original partner. Some binaries form through three-body interactions, where a passing star injects energy into a pair, stabilizing their orbit. These processes happen constantly, creating a self-sustaining population of stellar pairs that wouldn't survive in less crowded parts of the galaxy. But binaries don't just exist in globular clusters, they dominate them. Their gravitational interactions act like cosmic furnaces, pumping energy into the cluster and preventing it from collapsing under its own weight. This phenomenon, known as dynamical heating, works like this. When a tight binary encounters a single star, the interloper often gets flung away at high speed, carrying energy with it. Meanwhile, the binary recoils in the opposite direction, its orbit sometimes tightening in the process. It's a chaotic game of gravitational ping-pong, where every collision redistributes energy and keeps the cluster's core hot and puffed up. The most extreme cases involve hard binaries, pairs with orbits so tight they're practically touching. These systems pack enough gravitational punch to slingshot other stars to incredible velocities, some even fast enough to escape the cluster entirely. Over time, this process can completely reshape a globular cluster, ejecting stars into the galactic halo while hardening the remaining binaries into near indestructible configurations. Yet even these cosmic powerhouses aren't invincible. Some binaries meet catastrophic fates, merging into single, oversized stars or getting ripped apart by black holes. Others spiral closer and closer until they collide in spectacular flashes of light, creating blue stragglers or even exotic objects like millisecond pulsars. Every interaction leaves its mark, carving the cluster's structure into something no simple model could predict. What's truly mind-bending is how these binary systems influence the cluster's lifespan. Without them, simulations show globular clusters would collapse into ultra-dense cores far sooner, their stars crammed together like sardines. Instead, binaries act as cosmic shock absorbers, prolonging the chaos and ensuring these ancient star cities burn bright for billions of years longer than they should. They're not just inhabitants of globular clusters, they're the engines that keep them alive. Among the many chemical oddities found in globular clusters, none is more striking than the oxygen-depleted stars, stellar anomalies whose atmospheres contain shockingly low levels of one of the universe's most abundant elements. These stars shouldn't exist according to standard stellar models, yet there they are, burning defiantly with atmospheres nearly devoid of oxygen while swimming in sodium and aluminum. It's as if someone selectively removed a key ingredient from the cosmic recipe, leaving behind a baffling chemical signature that points to a dramatic chapter in these clusters' turbulent histories. The smoking gun lies in the ashes of ancient supernovae. When massive stars explode, they flood their surroundings with oxygen-rich material, so finding stars starved of this element suggests something intervened, scrubbing it from their birth environment. One compelling theory points to a phenomenon called supernova pollution, where an early generation of stars died in ultraviolet explosions, their remnants mixing unevenly with the cluster's remaining gas. Imagine a celestial bakery where one batch of bread dough gets contaminated with salt. Every loaf baked afterward would carry that same imbalance. In this case, the salt is sodium and aluminum, elements produced in staggering quantities by specific types of supernova, while oxygen gets mysteriously suppressed. But the plot thickens. These oxygen-poor stars aren't randomly scattered, they're often clumped together in distinct groups within their clusters, like neighborhoods in a city where everyone shares the same strange accent. This pattern hints at localized enrichment events, pockets of gas chemically altered before new stars formed. Some researchers propose that supernova from the cluster's first massive stars didn't distribute their debris evenly. Instead, their explosive energy might have carved out bubbles in the gas, creating zones of varying chemistry where later generations of stars condensed. Picture a polluted lake where certain coves collect more industrial runoff than others. Those sheltered spots would breed fish with radically different biology than the rest of the water. The most intriguing twist, the oxygen anomaly isn't just a relic. It's a clue about how globular clusters built themselves over time. Unlike galaxies, which continuously draw in fresh gas from the cosmos, these clusters had to recycle their own star stuff, creating new generations from the ashes of the old. The oxygen-depleted stars are evidence of that messy recycling process, where earlier supernova didn't just contribute elements, they actively withheld them, creating chemical imbalances that persist for billions of years. It's cosmic thriftiness taken to the extreme, a closed system where nothing goes to waste, not even the absence of an element. This discovery does more than rewrite stellar chemistry. It reshapes our understanding of how complex these clusters truly were in their youth. Far from being simple factories churning out identical stars, they were dynamic ecosystems where every explosion, every collision, and every mixing of gases left an indelible mark. The oxygen-poor stars are more than oddities, they're time capsules, preserving the violent and unpredictable conditions of a universe learning how to build itself. And with each new observation, they remind us that even the smallest chemical quirks can tell the grandest cosmic stories. Globular clusters have been caught emitting something far more energetic than starlight, mysterious surges of gamma rays that defy simple explanation. The Fermi Space Telescope first detected this strange glow, mapping excess high-energy radiation emanating from several clusters, with no obvious cosmic culprit behind it. These aren't fleeting bursts but persistent, diffuse halos of gamma radiation, as if the clusters are bathed in an invisible, radioactive fog. The discovery sent shockwaves through astrophysics because the leading explanations, dark matter annihilation or an improbable density of pulsars, both require rethinking how these ancient structures operate. Dark matter offers the most tantalizing possibility. Theoretical models suggest that if dark matter particles collide and annihilate in a cluster's dense core, they could produce gamma rays as a byproduct. Picture a cosmic power plant running on invisible fuel, its exhaust streaming across the electromagnetic spectrum. The cluster's strong gravitational fields would naturally concentrate dark matter, making them ideal hunting grounds for this elusive signal. But here's the catch, the gamma-ray excess doesn't perfectly match predictions. The energy spectrum is too smooth, lacking the sharp spikes expected from certain dark matter models. It's like finding fingerprints at a crime scene that don't match any known suspect. Then there's the pulsar hypothesis. Globular clusters are neutron star goldmines, and millisecond pulsars rapidly spinning, magnetized remnants emit gamma rays as they whirl. With thousands of these objects potentially crammed into a single cluster, their combined output might explain the glow, but the math is staggering. To match Fermi's observations, some clusters would need hundreds or even thousands of previously undetected pulsars, far more than current surveys suggest exist. It's the astronomical equivalent of discovering a hidden city beneath a familiar town possible, but requiring extraordinary evidence. The plot thickens when you examine which clusters glow and which don't. Surprisingly, the gamma-ray excess appears strongest in clusters with the highest encounter rates, places where stars and presumably pulsars frequently interact. This correlation hints that dynamic processes like stellar collisions or binary formations might be supercharging particle acceleration in ways we don't fully understand. Imagine a celestial particle accelerator where stars and magnetic fields conspire to boost radiation to extreme energies. What's truly bizarre is that no single theory fully explains all the data. Some clusters fit the dark matter narrative better, while others align with pulsar populations. A few, like M54, straddle the line, their gamma rays possibly arising from a mix of both, or something entirely unexpected. The mystery has grown so compelling that new telescopes are being trained on these clusters, searching for faint X-ray counterparts or subtle pulsar signatures that could break the stalemate. One thing's certain: whether the answer lies in the invisible hand of dark matter or the frenetic spin of hidden pulsars, globular clusters are once again proving to be cosmic enigmas. Their gamma-ray glow is more than an astronomical curiosity, it's a beacon, drawing us deeper into the unresolved questions at the heart of modern astrophysics. And with every new observation, we edge closer to answers that might rewrite not just the story of these clusters, but our understanding of the universe's most elusive forces. Among the countless globular clusters dotting our galaxy, a rare few stand out by breaking one of astronomy's most fundamental rules. They look far too young for their age. Take NGC 6791, a celestial rebel that shines with the vigor of a cluster half its years. While most globular clusters are ancient relics over 10 billion years old, this outlier burns with stars that appear fresh and lively, as if time forgot to take its toll. The contradiction is staggering. How could a structure this old host stars that seem to have skipped the aging process entirely? The answer lies in NGC 6791's unusual history. Unlike typical globular clusters that formed in a single burst, this one experienced multiple waves of star birth, with younger generations mixing among the ancient ones. Imagine finding a medieval castle with a modern skyscraper built into its courtyard. That's the kind of chronological whiplash astronomers face here. The later star-forming episodes pumped fresh gas into the system, creating stellar newcomers billions of years after the cluster's initial formation. But where did this extra gas come out? The leading theory suggests the cluster might have cannibalized a passing gas cloud or even a smaller star cluster, stealing the raw materials needed to spark new star formation. Chemistry tells an even stranger tale. While most globular clusters have metal-poor stars, relics from the early universe, and you see 6791 stars are rich in heavier elements like iron, a signature of more recent cosmic recycling. This suggests the cluster didn't just form new stars, it did so from gas already seeded with metals by earlier supernovae. It's like finding a sealed cave painting where part of the artwork was clearly touched up with modern paint, evidence of two distinct eras preserved in one place. The most mind-bending implication: NGC 6791 might not be alone. A handful of other clusters show similar, youthful traits, hinting that globular clusters could have more complex life cycles than we ever imagined. Some might have prolonged star formation through galactic collisions, while others could have drifted through gas-rich regions, gathering material like cosmic sponges. Each one challenges the old assumption that globular clusters are frozen in time, forcing us to see them as dynamic systems capable of reinventing themselves across eons. What makes these clusters truly special isn't just their defiance of age expectations, it's the window they offer into how stellar systems evolve under extreme conditions. They prove that even the oldest structures in the universe can find ways to cheat time, rewriting their destinies with every stolen cloud of gas or stolen cluster encounter. And as telescopes uncover more of these anomalies, we're left wondering just how many other cosmic rule breakers are hiding in plain sight, their stories waiting to shake the foundations of astrophysics all over again. Hidden deep within globular clusters, some of the universe's most precise timekeepers spin at impossible speeds, millisecond pulsars, neutron stars whirling hundreds of times per second with a stability that rivals atomic clocks. These cosmic tops didn't start out this fast. Born from the explosive deaths of massive stars, they began as slow rotators, barely completing a few turns per second. But in the crowded stellar neighborhoods of globular clusters, they found a shortcut to extreme speed through a process as violent as it is elegant: cosmic theft. Picture a gravitational vampire, a dense neutron star locked in orbit with a companion star, relentlessly siphoning gas from its neighbor. As stolen matter spirals onto the pulsar's surface, it transfers angular momentum like a figure skater pulling in their arms to spin faster, accelerating these stellar corpses to mind-bending velocities. The record holder, PSRJ 1748 plus 2446 AD in the cluster M28, spins 716 times per second. At that rate, its surface moves at roughly 15% the speed of light. Yet despite their dizzying rotations, these pulsars emit radio beams with metronomic precision, some varying by less than 1/1000th of a second over decades. This makes them unparalleled tools for testing Einstein's theory of general relativity. When a pulsar orbits another dense object, like in the famous binary system PSRB 1620-26 in M4, the extreme gravity warps spacetime, causing detectable delays in the pulsar's ticks. These delays match Einstein's predictions with staggering accuracy, effectively turning globular clusters into cosmic laboratories for fundamental physics. But millisecond pulsars aren't just scientific instruments, they're survivors of stellar chaos. In most environments, a lone neutron star would never encounter enough donated matter to reach such speeds. Globular clusters, however, are binary star factories where close encounters frequently pair neutron stars with donor stars. Some pulsars even swap partners multiple times, like dancers in a gravitational ballroom, each new companion offering fresh fuel for acceleration. The most extreme cases, like the Black Widow pulsars, consume their companions entirely, leaving behind ghostly traces of vaporized stellar material. What makes these objects truly extraordinary is their dual nature, both relics of stellar death and engines of new discovery. By measuring subtle variations in their pulses, astronomers have uncovered hidden planets orbiting pulsars, mapped the cluster's gravitational fields, and even detected the faint ripples of gravitational waves distorting our galaxy. Every rotation encodes information about the cluster's history, composition, and future, making these spinning stellar corpses some of the universe's most articulate storytellers. And with new radio telescopes coming online, we're poised to uncover even more of their secrets, one precise tick at a time. Globular clusters were once thought to be textbook examples of stellar uniformity, tightly packed families of stars born from the same primordial cloud at the same cosmic moment. But when astronomers trained their spectroscopes on these ancient gatherings, they uncovered a chemical rebellion. Certain clusters, like Omega Centauri and M54, host stars with wildly different ion contents, some containing 10 times more than their neighbors. This isn't just a minor variation, it's a fundamental crack in the single population paradigm that dominated cluster science for decades. If all these stars form together from the same gas, why do their metallicities scatter across the spectrum like paint splatters on a perfect canvas? The answer lies in the cluster's chaotic youth. Iron, forged in the hearts of massive stars and scattered by supernova, acts as a cosmic timestamp. In a true single-generation cluster, every star should share nearly identical iron levels, like siblings inheriting the same family traits. But the outliers tell a different story. Their iron-rich compositions suggest later generations formed from gas polluted by supernova from earlier stellar cohorts. Imagine a snowball rolling downhill, gathering layers of dirt with each revolution. Similarly, these clusters didn't form in one pristine collapse. They grew through multiple waves of star birth, each new generation enriched by the ashes of its predecessors. The smoking gun comes from how these iron variations are distributed. In Omega Centauri, stars split into at least 3 distinct iron populations, each separated by gaps too large to explain by random sampling. It's as if the cluster hit pause on star formation multiple times, only to restart with fresh, chemically altered gas. One theory suggests the cluster collided with giant molecular clouds, gaining new raw material for additional star-making sessions. Another posits that it began as the core of a dwarf galaxy, a system large enough to retain supernova debris and recycle it into new stellar creations. What's truly revolutionary is how this discovery rewrites the rules of cluster formation. No longer can we view globular clusters as simple, one-shot stellar factories. They're dynamic systems that might have cannibalized smaller clusters, absorbed passing gas clouds, or even merged with other structures, each event leaving behind chemical breadcrumbs in the stars we see today. The iron discrepancies aren't anomalies. They're forensic evidence of a turbulent past, proving these quiet-looking clusters were once cosmic battlegrounds where gravity and chemistry waged an endless war for dominance. This shift in understanding ripples far beyond cluster physics. If globular clusters can harbor multiple generations of stars, what does that mean for our models of galaxy formation? Could some dwarf galaxies long thought to be simple, inefficient star formers actually be scaled-up versions of these complex globulars? The iron-rich stars whisper tantalizing possibilities, reminding us that even the oldest objects in the universe still have secrets to spill. Every new spectroscopic survey peels back another layer, revealing a story far richer and far messier than anyone dared imagine. Globular clusters don't just shimmer with visible starlight, they crackle with high-energy X-rays, betraying the presence of bizarre cosmic duos called X-ray binaries. These systems, where a neutron star or black hole voraciously feeds on a companion star, should be rare. Yet in these ancient stellar metropolises, they're shockingly abundant. Some clusters host dozens where just 1 or 2 would be expected. It's like finding a bustling fast food district in what you thought was a retirement community. The reason? Sheer stellar overcrowding turns these clusters into cosmic mosh pits where gravitational encounters are constant and extreme partnerships form out of chaos. Take Terzan 5, a cluster so dense it glows like an X-ray beacon. Amid its million stars, astronomers have identified at least 34 X-ray binaries, a record-breaking concentration. In most galactic environments, such systems would be light-years apart. But here, stars orbit so closely that a neutron star can easily capture a passing neighbor, twisting their fates together in a deadly gravitational dance. Picture a crowded subway where every third passenger carries a flaring torch. That's the kind of relentless energy bombardment happening in these clusters. The process is as brutal as it is efficient. When 2 stars drift too close in the cluster's core, the heavier one, often already a stellar corpse, can strip gas from its companion. This stolen material spirals inward, heating to millions of degrees and unleashing X-rays bright enough to outshine entire galaxies. Some binaries flare episodically, their X-ray emissions spiking when fresh gas arrives. Others burn steadily, their accretion disks glowing like cosmic furnaces fed by an endless supply of stellar fuel. What's truly bizarre is how these systems shape their surroundings. X-ray binaries act like gravitational power tools, ejecting nearby stars at high speeds or flinging them into new orbits. Over time, their collective energy output can heat the cluster's core, preventing catastrophic collapse, a cosmic case of destruction preserving order. They're also stellar recycling plants. As the donor star gets devoured, its material might eventually form new planets or even future stars, seeding the cluster with fresh possibilities. The implications stretch far beyond these clusters. By studying X-ray binary populations, astronomers can gauge a globular cluster's dynamical age, how long its stars have been crashing into each other. Younger clusters might have fewer binaries, their stars still settling into gravitational equilibrium. Ancient ones like Terzan 5 or M15, where their X-ray excess like a badge of honor, proof of billions of years of stellar close encounters. Yet mysteries remain. Some clusters with similar densities host wildly different numbers of X-ray binaries, suggesting hidden factors at play. Could dark matter be influencing their formation? Or does the precise arrangement of black holes in the core dictate how many binaries survive? Every new observation peels back another layer, revealing these high-energy couples not as cosmic accidents, but as inevitable products of extreme stellar crowding, a reminder that in the universe's oldest neighborhoods, chaos and beauty are often one and the same. History has a way of swallowing celestial wonders whole, and globular clusters are no exception. Among the most haunting mysteries in astronomy are the lost clusters, those that vanished from observational records for decades, sometimes centuries, only to resurface like cosmic ghosts. Take Palomar 5, a cluster so thoroughly ravaged by the Milky Way's gravity that it's more stream than sphere, a shimmering trail of stars stretched across 30,000 light-years, slowly dissolving into the galaxy's halo. But this isn't just a tale of destruction, it's a window into how even the most resilient structures meet their end. The story of lost clusters often begins with human error. In the early days of telescopic astronomy, observers like William Herschel meticulously catalogued nebulae, faint smudges of light that included everything from galaxies to star clusters. But as telescopes improved, many entries were misclassified or forgotten. Some, like the bizarre case of Kopasov 1 and 2, were only rediscovered in the 21st century during automated sky surveys, their faint glow overlooked for generations. Others, like Georgovsky 1, spent years hiding in plain sight, disguised as dense star fields until modern spectroscopy revealed their true nature. These clusters weren't just lost, they were camouflaged, their identities erased by the limitations of early astronomy. Yet Palomar 5's fate is different. This cluster isn't missing, it's unraveling. Tidal forces from the Milky Way have siphoned away over 2/3 of its stars, leaving behind a skeletal core and twin tidal tails that stretch like celestial comet trails. Simulations suggest it has less than 1 billion years left before it's fully absorbed, its stars scattered across the galactic halo. But here's the twist, this destruction is birthing a new kind of structure. The cluster's escaping stars are forming one of the Milky Way's faintest streams, a river of stellar refugees tracing Palomar 5's orbital path. It's a cosmic metamorphosis, a globular cluster transforming into a stellar stream, rewriting its legacy even as it fades. What makes Palomar 5's story so compelling isn't just its demise, but what it reveals about the galaxy's appetite. The Milky Way is littered with the remnants of devoured clusters, their stars assimilated so thoroughly that only their chemical fingerprints remain. By studying Palomar 5 mid-dissolution, astronomers are glimpsing a process that's usually invisible, the final acts of a cluster's life. Its tidal tails act as a Rosetta Stone for decoding similar streams like the orphan GD1, which may be all that's left of a cluster long since consumed. The eerie beauty of these lost and dying clusters lies in their duality. They're both casualties and creators, their destruction seeding the galaxy with ancient stars. And as telescopes grow more sensitive, who knows how many other vanished clusters might reappear, their stories waiting to be told. Each rediscovery peels back another layer of cosmic history, proving that even in astronomy, the past is never truly gone, just hidden in the light. Globular clusters aren't just random swarms of stars, they contain celestial choreography so precise it defies belief. Deep within these ancient structures, astronomers have spotted groups of stars moving in perfect unison, their trajectories locked together like dancers in a cosmic ballet. These co-moving stellar squads share nearly identical velocities and spatial paths, suggesting they've traveled as a unit for billions of years. It's as if time itself froze these stars in formation, preserving their synchronized motion across eons while the rest of the cluster churns around them. The secret to this harmony lies in their shared origin story. Unlike solitary stars that wandered into the cluster's gravitational embrace, these co-moving groups likely formed together from the same dense molecular cloud. Picture a family of celestial siblings born from the same stellar nursery and bound by both genetics and gravity. Their synchronized paths act as cosmic DNA, revealing kinship that even spectroscopy can't always detect. Some groups contain just a handful of stars, while others, like the famous string of pearls in Omega Centauri, stretch across light years in flawless formation. But how do these fragile alliances survive the gravitational mayhem of a globular cluster? The answer lies in an astronomical phenomenon called dynamical friction. As stars orbit the cluster's core, gravitational interactions with neighbors gradually nudge lighter stars outward while heavier stars sink toward the center, a sorting process that takes eons. Co-moving groups often contain stars of similar mass, allowing them to migrate together like leaves floating on the same river current. Their shared momentum becomes a protective shield, helping them navigate the cluster's chaotic interior without being torn apart. Computer simulations reveal an even stranger twist. Some groups might be the remnants of smaller clusters consumed by the globular behemoth long ago. Like tree rings preserving a forest's history, these synchronized stars could be fossils of past mergers, their coordinated motions betraying their foreign origins. Others might have formed through more exotic processes, like the fragmentation of massive gas disks during the cluster's violent youth. The implications stretch far beyond stellar dynamics. These co-moving groups serve as cosmic time capsules, preserving information about the cluster's formation that would otherwise be lost. By tracking their motions, astronomers can reconstruct gravitational events that shaped the cluster billions of years ago: collisions, close encounters, even the gravitational ripples from long-vanished black holes. Each synchronized group is a living archive, its movements encoding secrets about the universe's most chaotic environments. And as telescopes grow more precise, revealing finer details of stellar motions, we're on the verge of decoding these celestial synchronies like never before, peeling back layer after layer of the universe's hidden choreography. Among the many chemical riddles hidden in globular clusters, none is more perplexing than the case of the missing lithium, a cosmic whodunit that reaches back to the very first minutes of the universe. Lithium, the third lightest element forged in the Big Bang's primordial furnace, should exist in predictable amounts in every ancient star. Yet when astronomers peer into these clusters, they find stars with lithium levels up to 200 times lower than expected. It's as if someone methodically scrubbed this element from stellar atmospheres, leaving behind a fingerprint that contradicts our most fundamental models of cosmic chemistry. This discrepancy cuts to the heart of Big Bang nucleosynthesis, the process that created the first elements. According to theory, the newborn universe cooked up precise ratios of hydrogen, helium, and trace amounts of lithium. These predictions match what we see in most ancient stars, except in globular clusters. There, lithium depletion follows no clear pattern. Some stars retain normal levels, while their immediate neighbors are practically lithium-free, like empty cups at a cosmic tea party where the beverage was unevenly poured. What could explain this selective disappearance? One leading suspect lurks inside the stars themselves. Unlike hydrogen and helium, lithium is fragile. It breaks apart at temperatures just over 2.5 million degrees. In stars with deep convective zones, where material cycles between surface and core, lithium can be transported downward and destroyed in the hotter interior. Picture a snowflake tossed into a furnace. That's lithium's fate in these stellar cauldrons. But this explanation only fits some cases. Certain globular cluster stars have the right structure to preserve lithium, yet still show depletion, suggesting external factors at play. Enter the primordial pollution theory, a radical idea that early generations of stars might have chemically altered the cluster's gas before later stars formed. The first supernova in these clusters could have unleashed floods of radiation and particles, battering lithium nuclei and breaking them apart in interstellar space. Think of it as cosmic vandalism, where the element was erased before newer stars could inherit it. Supporting this, some lithium-poor stars also show odd abundances of beryllium and boron, elements similarly vulnerable to radiation damage. Yet the plot thickens when we examine clusters like M4, where lithium levels vary wildly between otherwise identical stars. This suggests another culprit: stellar encounters. In these dense environments, close passes between stars might strip away outer layers where lithium concentrates, like thieves stealing only the top layer of a treasure chest. Computer simulations show such gravitational theft could leave some stars lithium depleted while sparing others a perfect match for the erratic patterns we observe. The implications stretch far beyond stellar chemistry. If lithium can vanish so unpredictably, it challenges our ability to use it as a cosmometer, a tool for measuring the universe's earliest moments. Globular clusters, once seen as pristine windows into the primordial past, now appear to be messy laboratories where lithium was altered, destroyed, or hidden by processes we're still unraveling. Each lithium-deficient star is a clue in this cosmic detective story, whispering secrets about how the first element survived, or didn't, in the universe's most chaotic neighborhoods. Perhaps the most tantalizing possibility is that we're glimpsing physics beyond standard models, exotic particle interactions, or unknown nuclear processes that preferentially destroy lithium in certain environments. Whatever the ultimate answer, these clusters remind us that even the simplest atoms can hold the keys to profound mysteries. As telescopes probe deeper into stellar atmospheres, every new lithium measurement sharpens our view of the universe's first 3 minutes and the 13 billion years of stellar shenanigans that followed. White dwarfs, the glowing embers of dead stars, should be the universe's most predictable clocks. These dense stellar remnants, having exhausted their nuclear fuel, slowly fade as they radiate heat into space. Their cooling rate follows well-understood physics, making them cosmic chronometers used to date star clusters. But globular clusters have thrown a wrench into this elegant system. Their white dwarfs are cooling far slower than theory predicts, lingering at higher temperatures like stubborn coals that refuse to die. This anomaly might signal hidden physics at play, perhaps even dark matter's elusive influence altering how heat escapes these ancient stellar corpses. The mystery first emerged when astronomers compared white dwarfs in globular clusters to their isolated counterparts in the galactic field. At the same age, cluster white dwarfs consistently appear hotter and brighter, some by startling margins. It's as if these stellar remnants have discovered some secret energy reserve, stretching their twilight years beyond all reasonable limits. Traditional explanations fell short. Could lingering nuclear reactions be delaying their cooling? Unlikely. White dwarfs lack the necessary fuel, maybe gravitational energy from settling material. Calculations show this contributes minimally. The discrepancy only deepened with better observations, pointing toward something fundamentally missing from our models. Enter dark matter, the universe's most pervasive mystery. If globular clusters contain even small concentrations of this invisible substance, its particles might interact with the white dwarfs in unexpected ways. One provocative theory suggests that dark matter particles could become trapped in a white dwarf's incredibly dense interior, accumulating over billions of years. As they collide and annihilate, they'd release energy, effectively providing a hidden heat source. Imagine a car engine that shouldn't run yet does because someone secretly keeps adding fuel. The effect would be subtle but cumulative, gently nudging the cooling curve off its expected path. But dark matter isn't the only suspect. Some physicists speculate that the anomaly might reveal exotic states of matter unique to these extreme environments. At the crushing densities inside white dwarfs, where a teaspoon of material weighs as much as an elephant, quantum effects could produce unexpected phenomena. Perhaps electrons form previously unknown collective states that slow heat loss, or crystalline structures in the star's carbon-oxygen interior trap thermal energy like microscopic insulation. Even the shape of spacetime itself might play a role. Strong gravitational fields could subtly alter how photons escape, effectively trapping heat longer than anticipated. The implications stretch far beyond stellar physics. If dark matter is truly influencing white dwarf cooling, these clusters could become invaluable dark matter detectors. They're white dwarfs acting as ultra-sensitive gauges for invisible particles. Conversely, if exotic matter physics explains the anomaly, we might need to revise our understanding of degenerate matter under extreme conditions. Either outcome would rewrite textbooks. Compellingly, the effect varies between clusters, hinting that local conditions matter. In clusters with denser cores or stronger gravitational fields, the cooling delay appears more pronounced. This clustering-specific pattern suggests an environmental factor, something tied to the unique ecology of globular clusters rather than a universal white dwarf trait. Future observations could map this variation, potentially isolating the mechanism behind the anomaly by comparing clusters with different ages, densities, and chemical compositions. For now, the white dwarf cooling anomaly remains one of globular clusters' most persistent puzzles. These fading stars should be simple to understand stellar retirement homes where physics follows well-worn rules. Instead, they're whispering tantalizing hints that even in death, stars might hold secrets that challenge our grasp of the cosmos. Until we solve this riddle, every anomalously bright white dwarf serves as a reminder. The universe enjoys undermining our certainties, one cooling curve at a time. Globular clusters are supposed to be celestial objects governed by straightforward physics where the mass you see is the mass you get. But then there's M53, a cosmic rebel that refuses to play by the rules. This cluster, along with a handful of others, exhibits a gravitational pull that outstrips the combined heft of all its visible stars. It's as if an invisible hand lurks within, bending starlight and twisting orbits in ways that make no sense without extra mass. The strangest part, unlike galaxies where dark matter neatly explains such discrepancies, globular clusters aren't supposed to harbor this enigmatic substance. So what's really going on inside these dark clusters? The mystery starts with stellar motions. When astronomers track how stars zip around M53's core, their velocities suggest a gravitational field far stronger than the cluster's luminous matter can account for. If only visible stars were present, outer stars should orbit more sluggishly, like cars coasting on an empty highway. Instead, they whip around as if tethered to something unseen. Traditional explanations fall short. Stellar mass black holes could contribute, but simulations show they'd either sink to the core or get ejected, leaving no trace in the outer regions. Neutron stars and white dwarfs, common cluster denizens, are too few to fill the gap. Even rogue planets or brown dwarfs, often invoked as missing mass candidates, can't bridge the chasm between prediction and observation. This leaves two unsettling possibilities. Either our measurements are fundamentally flawed, a tantalizing but unlikely prospect given multiple independent studies, or we're glimpsing physics beyond the standard model. One radical theory posits that globular clusters could contain dark matter light, a variant of the elusive substance that clumps differently than the dark matter saturating galaxies. Imagine a cosmic seasoning that only appears in certain celestial recipes, subtly altering gravity's grip without the usual galactic scale effects. Supporting this, some clusters with mass discrepancies also emit faint gamma rays, a potential dark matter signature. But the plot thickens when comparing clusters. Not all exhibit these anomalies, and the discrepancies vary wildly. M53's missing mass is modest compared to, say, NGC 5897, where the mismatch approaches 80%. This inconsistency suggests environmental factors at play, perhaps collisions or tidal interactions that stripped away normal matter while leaving dark components behind. Alternatively, could these clusters be infiltrated by primordial black holes, remnants of the early universe hiding in their cores? These invisible gravitational anchors would explain the extra pull without requiring new physics, but their existence remains unproven. The implications ripple far beyond stellar dynamics. If globular clusters truly harbor unconventional dark matter, they could be cosmic petri dishes for testing theories that larger galaxies can't. Their simplicity, lack of gas, dust, or recent star formation makes them cleaner laboratories than messy spirals. Conversely, if the anomalies stem from overlooked astrophysics, like poorly modeled stellar interactions or unseen populations of compact objects, it would force a re-evaluation of how we weigh the universe's building blocks. For now, M53 and its enigmatic kin remain outliers, celestial troublemakers refusing to fit neatly into our cosmic framework. Every new observation peels back another layer of the mystery, proving that even the universe's oldest structures can still spring surprises. Whether the answer lies in shadowy particles or mundane measurement quirks, one thing's certain: dark globular clusters are rewriting the rules of stellar gravity, one perplexing orbit at a time. Globular clusters should be retirement homes for aging stars, filled with crimson-hued red giants puffing out their final breaths in slow, luminous farewells. Yet when astronomers count these elder stars in certain clusters, the numbers don't add up. Some are missing up to half the red giants predicted by stellar evolution models. It's as if these clusters have a cosmic filter, siphoning away their senior stars before they can reach their grand finale. The discrepancy points to something far more dramatic than a simple counting error. Either these stars are shedding mass at unprecedented rates, or the clusters themselves are violently ejecting their elders before they can fully evolve. The mystery centers on a phase of stellar life that should be unavoidable. When a star like our Sun exhausts its hydrogen fuel, it swells into a red giant, growing hundreds of times larger and glowing with a distinctive ruddy light. In globular clusters, where stars are all roughly the same age, the number of red giants should follow a predictable curve based on mass and metallicity. But in clusters like NGC 6306 and M10, the curve plummets where it should peak. Stars aren't just skipping the red giant phase, they're vanishing from it altogether. One explanation lies in extreme mass loss. Normally, red giants shed their outer layers gradually, forming beautiful planetary nebulae before collapsing into white dwarfs. But in these clusters, something might be stripping stars bare long before they reach full giant status. Picture a tree in a windstorm losing not just leaves but entire branches, stellar atmospheres ripped away by brutal gravitational tides or relentless stellar winds. Supporting this, some clusters show excess hot helium stars, the exposed cores of what should have been red giants, their fluffy outer layers already torn off. These naked cores burn hotter and die faster, explaining why the expected red giants never materialized. But mass loss alone can't account for the scale of the shortage. Enter the disruptive dynamics of dense cluster cores. In these crowded stellar metropolises, close encounters are inevitable, and for bloated red giants, they're often fatal. A passing star or black hole can tear material from a giant's distended atmosphere like gravitational theft. Even worse, a direct collision could shatter the star entirely, scattering its remains before it completes its evolution. Simulations show these interactions could eject hundreds of red giants over a cluster's lifetime, flinging them into the galactic halo or outright destroying them. The most intriguing evidence comes from clusters with blue tails, unexpected populations of hot, young-looking stars. These might be the offspring of disrupted red giants, their stripped material igniting new star formation in a morbid cosmic recycling program. It's a stellar circle of life where death begets new birth, but the original giants leave no trace behind. This missing red giant problem isn't just about stellar demographics, it's a window into the violent ecology of globular clusters. These environments don't just cradle stars, they sculpt them, sometimes truncating their life cycles entirely. By studying the gaps in the red giant population, astronomers are piecing together a hidden history of gravitational theft, stellar collisions, and mass loss on scales we never imagined. Every absent giant is a silent witness to the chaos lurking within these ancient star cities, proving that even the universe's oldest neighborhoods are anything but peaceful. Deep in the hearts of globular clusters, stars are pulling off one of the universe's greatest disappearing acts, vanishing from their own life cycles. Normally, when a sun-like star exhausts its hydrogen fuel, it undergoes a spectacular internal rebellion called the helium flash, a violent thermal runaway where helium ignites explosively in the star's core. This cosmic fireworks display should be unavoidable for low-mass stars, a defining milestone in their evolution. But in certain globular clusters, astronomers have caught stars red-handed skipping this critical phase entirely, burning helium quietly as if the rules of stellar physics simply don't apply. The smoking gun comes from the cluster's color magnitude diagrams. Stellar Census reports that plot brightness against temperature, where there should be a distinct bump marking stars transitioning through the helium flash. Some clusters like M3 show a suspicious gap instead. It's as if nature pressed fast forward, with stars jumping straight to the next evolutionary stage without the customary detonation. This isn't just a case of missing data. The stars are demonstrably different, with chemical signatures proving they fused helium without the predicted pyrotechnics. What could possibly let stars dodge this cosmic rite of passage? The leading theory points to an astronomical loophole: stellar interactions unique to globular clusters' extreme environments. In these crowded stellar cities, stars frequently exchange mass through binary transfers or close encounters. A star that would typically experience a violent helium flash might instead receive fresh hydrogen fuel from a companion, stabilizing its core and preventing the runaway ignition. Picture a time bomb being defused at the last second by an unseen hand, except here, the hand belongs to a neighboring star, donating just enough material to keep the peace. Alternatively, some stars might experience helium flashes so mild they barely register. In metal-poor clusters, environments where stars form with fewer heavier elements, the cores behave differently under extreme pressure. Computer simulations reveal that under these pristine conditions, helium can ignite more gradually, like a damp fuse sputtering rather than exploding. The result, a stellar evolution pathway that sidesteps the drama entirely, rewriting the textbook transition from red giant to horizontal branch star. The implications ripple far beyond academic curiosity. The helium flash acts as a critical reset button for stars, determining their size, temperature, and lifespan. Stars that skip or alter this process end up with radically different futures, some burning hotter and dying younger, others lingering for extra billions of years. If our models have overlooked these alternate pathways, we might be misjudging the ages of entire clusters or misreading the cosmic clock that tracks galactic evolution. Even more provocative is what these outliers suggest about stellar diversity. Globular clusters were once considered laboratories of uniformity, where stars shared nearly identical compositions and life stories. But the helium flash rebels prove that even in these ancient communities, stars find ways to break the mold. Whether through gravitational theft, chemical quirks, or sheer brute force crowding, they carve out exceptions to the universe's supposed rules, reminding us that in the cosmic dance of physics and chance, there's always room for surprises. Globular clusters were once considered universal stellar metropolises following the same blueprint across the cosmos. But when astronomers peered beyond the Milky Way, they uncovered a menagerie of bizarre outliers that defy expectations. Take the gargantuan clusters orbiting Andromeda, our galactic neighbor's version of Omega Centauri, which outshine their Milky Way counterparts by a factor of 10. These cosmic leviathans burn so intensely that their combined light rivals small galaxies, packed with stars numbering in the tens of millions rather than the mere hundreds of thousands typical in our own backyard. What cosmic conditions birthed these behemoths? The answer may lie in their violent origins. Many appear to be the ravaged cores of dwarf galaxies shredded during collisions, their outer stars stripped away while their dense hearts survived. Then there's the blue globular phenomenon in the Triangulum galaxy, clusters so saturated with young, hot stars they glow an eerie azure against the cosmic darkness. Unlike the ancient red and gold swarms of the Milky Way, these outliers formed relatively recently, some as late as 2 billion years ago. Their existence shreds the old assumption that globular clusters are exclusively fossils of the early universe. One theory suggests they ignited during Triangulum's chaotic merger history, where colliding gas clouds triggered delayed bursts of star formation. Others propose their second-generation clusters, born from the recycled debris of older clusters torn apart by galactic tides. But the real oddballs lurk in galaxy clusters like Virgo, where ultra-compact dwarfs blur the line between star cluster and miniature galaxy. These objects, some only 50 light-years across, pack stellar densities 1,000 times greater than Milky Way globulars. Their stars orbit so closely that collisions are inevitable, creating freakishly massive stellar zombies through relentless mergers. Stranger still, many contain supermassive black holes at their centers, features unheard of in local globulars. Their discovery forces us to ask, is there a fundamental size or density limit for what we call a star cluster? The most puzzling disparities emerge when comparing chemical compositions. While Milky Way globulars are famously metal-poor, those orbiting giant elliptical galaxies often show iron abundances rivaling the Sun's. This suggests they formed later, from gas already enriched by generations of earlier stars. Some, like the clusters around Centaurus A, even host multiple stellar populations with drastically different metal contents, a feature once thought unique to Omega Centauri. The implication: globular clusters might not be a single class of object, but the end products of vastly different formation pathways depending on their galactic environment. Perhaps the most radical revelation comes from the Fornax dwarf spheroidal, a tiny satellite galaxy of the Milky Way hosting globulars that move in bizarre, counter-rotating orbits. Unlike our galaxy's clusters, which orbit neatly along the galactic plane, Fornax's clusters seem to tumble chaotically, as if hurled into space by some ancient gravitational slingshot. This kinematic anarchy hints that globular clusters can be immigrant populations, captured during galactic collisions rather than born in place. These intergalactic comparisons don't just expand our catalog of cosmic oddities, they force us to rethink what globular clusters truly are. No longer can we view them as simple, ancient relics following universal rules. Instead, they're chameleons, their properties shaped by the galaxies they call home. From youthful blue swarms to black hole-infested ultra-dwarfs, each discovery peels back another layer of complexity, revealing a universe far more inventive and far less predictable than we ever imagined. Globular clusters have long been known for their dense collections of ancient stars, but they also harbor a more elusive cosmic trick: the ability to warp space itself. When light from distant galaxies passes near these clusters, it doesn't travel in a straight line. Instead, the cluster's immense gravity bends the light's path, acting like a natural telescope that magnifies and distorts the background universe. This phenomenon, called gravitational lensing, is one of Einstein's most dramatic predictions in action. Yet some globular clusters bend light in ways that shouldn't be possible given their visible mass. The distortion is too strong, too uneven, as if hidden weights are embedded in their cores, tugging on space-time like invisible anchors. Hubble's sharp eye has captured some of the most striking examples of this anomaly. In the cluster M22, for instance, lensed images of distant galaxies appear stretched into faint, ghostly arcs around the cluster's edges, a telltale sign of intense gravitational bending. But when astronomers calculated the mass required to create these arcs using the stars alone, the numbers fell short. Something else, something unseen, must be contributing to the gravitational pull. The discrepancy isn't minor. In some cases, the lensing effect implies up to 50% more mass than the visible stars can account for. The leading explanation points to dark matter, the mysterious, invisible substance that permeates galaxies. But here's the twist: globular clusters aren't supposed to contain significant amounts of it. Unlike sprawling galaxies, which rely on dark matter to hold their shape, these compact star swarms were thought to be held together by stars and stellar remnants alone. Yet the lensing observations suggest otherwise. Could these clusters have retained small halos of dark matter from their formation, or does their environment somehow concentrate it in unexpected ways? Another possibility involves black holes, not just one or two, but entire populations lurking in the cluster's core. Intermediate mass black holes, stellar mass black holes, or even rogue planetary remnants could collectively add enough unseen mass to explain the extra lensing power. Imagine a cosmic game of hide and seek, where dark, compact objects skew the cluster's gravitational signature without emitting light. The implications ripple far beyond these clusters. If globular lenses reveal hidden mass, they could help map dark matter's distribution on scales too small for galaxies to resolve. They might also settle debates about whether dark matter is clumpy or smoothly distributed at these densities. Every distorted background galaxy, every unexpected arc of light, is a clue, a fingerprint left by the universe's most elusive ingredient. And with next-generation telescopes set to probe these clusters in even greater detail, we may finally crack the code of their gravitational secrets. Globular clusters may appear eternal, their ancient stars locked in an endless gravitational dance, but like all things in the universe, they're living on borrowed time. The question isn't if these stellar cities will meet their end, but how. Will they slowly evaporate, their stars stripped away one by one, collide and merge into superclusters? Or be violently shredded by the galaxies they orbit? The answers lie in a cosmic tug of war between gravity, time, and chaos, playing out over timescales so vast they dwarf human history. Take evaporation, the slow, inevitable leak of stars from a cluster's gravitational grip. In the crowded core, stars constantly trade energy through gravitational encounters. Over billions of years, lighter stars gain enough velocity to escape, like particles boiling off a liquid surface. Simulations suggest this process could reduce a cluster to a skeleton crew in under 100 billion years, leaving behind only a tight knot of black holes and neutron stars. But there's a twist. Clusters orbiting galaxies like the Milky Way face additional threats. Every close pass to the galactic center yanks stars away through tidal forces, accelerating their demise. Palomar 5, with its sprawling tidal tails, offers a preview, already more stream than cluster, its stars dissolving into the galactic halo like sugar in water. Yet some clusters might cheat fate through mergers. In galaxy collisions, globular clusters can slam together, their stars mixing into a single, brighter structure. Omega Centauri's complex stellar populations hint at such a violent past, likely the mashed-up remains of multiple smaller clusters. Imagine two snow globes shaken and poured into one, chaotic in the moment but settling into a new equilibrium. Theoretically, these mergers could birth superclusters with masses rivaling small galaxies. But even these titans wouldn't last forever. Given enough time, gravitational waves from orbiting black holes would sap their energy, causing gradual collapse. The most dramatic endings belong to clusters venturing too close to galactic centers. There, supermassive black holes lurk, capable of tearing clusters apart in a process called spaghettification. Stars near the black holes more stretch into thin streams, while those farther out scatter like billiard balls in a broken rack. The cluster doesn't just fade, it erupts, its stars becoming eccentric loners orbiting the galaxy's heart. This may explain why galaxies like Andromeda have fewer globular clusters near their cores. The black hole's appetite clears the neighborhood, but here's the wild card: dark matter. If some clusters retain invisible halos, as lensing anomalies suggest, this extra mass could armor them against evaporation or tidal destruction. A dark matter-rich cluster might outlive its peers by trillions of years, becoming a lone relic in an aging universe. Alternatively, dark matter interactions could hasten their collapse, depending on its properties, a reminder that the universe's most elusive substance might hold the keys to these structures' ultimate fates. What's certain is that globular clusters won't vanish quietly. Even in dissolution, they'll seed their host galaxies with ancient stars, chemically enriching future generations. Their deaths, whenever they come, will be less an ending and more a transformation, stellar souls returning to the cosmic sea from which they arose. And as the last clusters fade, they'll leave behind one final lesson. In the universe, nothing is permanent, but everything is recycled. From blue stragglers that burn too young to runaway stars flung across the galaxy at unimaginable speeds, globular clusters have spent decades rewriting the rules of astrophysics. These ancient stellar cities shouldn't hide black holes, yet intermediate mass monsters lurk in their cores. Their stars shouldn't vary so wildly in iron and oxygen, yet chemical anomalies paint a chaotic history of cannibalism and rebirth. They shouldn't harbor planets, yet worlds cling to existence in their chaotic orbits. Every corner of these clusters defies expectations, turning what we thought were simple cosmic relics into dynamic laboratories where physics gets pushed to its limits. Consider the paradoxes we've uncovered: clusters that appear older than the universe itself, ghostly tidal tails stretching across millennia, and white dwarfs that refuse to cool on schedule. Even their missing red giants and vanishing supernova remnants hint at processes we've yet to comprehend. And let's not forget the gamma-ray glow, an enigma that could point to dark matter or a hidden pulsar population, each possibility more thrilling than the last. These aren't just oddities, they're cosmic breadcrumbs leading us toward deeper truths about how galaxies form, how stars live and die, and perhaps even how dark matter sculpts the universe. What makes these discoveries so electrifying is how they force us to rethink the basics. Globular clusters were once considered predictable, uniform assemblies of ancient stars where nothing much happened. Now we know they're anything but. They're stellar graveyards and rebirth factories, demolition derbies and particle accelerators, all rolled into shimmering orbs of light. Every new observation peels back another layer, revealing complexities that challenge even our most advanced simulations. So here's the real wonder: after centuries of study, these clusters are still teaching us. They've become cosmic Rosetta Stones, helping decode everything from stellar evolution to the invisible scaffolding of the cosmos. And with next-generation telescopes set to probe deeper than ever, who knows what other secrets they'll surrender. Maybe you've got a favorite mystery: the rogue planets, the helium flash rebels, or those eerie radio whispers. Drop it in the comments and let's keep the conversation going. Because if there's one thing globular clusters have taught us, it's that the universe always has another surprise waiting, especially in its oldest, glittering neighborhoods. Stay curious.